All right, for those of you who don't know me, let me give you a little bit of background on me. Take about a minute. I started out in weather back in 1968. I was a newly commissioned naval officer, and they were starting a new program for meteorologists at Naval Postgraduate School in Monterey, California. So that's where I got my original training in meteorology. Then when I finished my active duty, I went to Rutgers University for graduate school and got my master's degree in meteorology. I worked for a private consulting firm in the Boston area until, in fact, we were the chief competitor to AccuWeather back in the mid 70s and early 80s. And because our managers were trying to undercut AccuWeather to get more clients, they ended up going bankrupt. So we all got laid off, and that's when I decided, well, let's go to Maine. So I came up here and I taught math and science in the Dexter school system until the early 2000s, and I decided I wanted to get back into forecasting weather, so I started my own little weather forecasting service out of my house. So to show you just what's going on today, oh, wait a minute. Oh, okay. This is today's weather map. I figured I'd start off by showing you what's going on around here today. Here's Maine, and here's central Maine right there. And there's a fairly strong high pressure system down over Pennsylvania, which is sending a lot of warm, humid air, if you follow the pointer there, into this area. And that's going to be with us right through tomorrow. And then after that, this little low pressure system here off Cape Hatteras is going to bring us some much needed rain for Saturday. You'll notice that this whole area of the eastern United States is pretty much having the same weather, as the flow of air is just like this. And it's quite a bit drier if you go out to the west here. And this is the forecast that I put out this morning. In fact, Pat has probably already read it. And you can see where I talked about early morning fog breaking up and becoming mostly clear, partly cloudy, still hazy and humid. And I stuck in a 10% chance for an isolated afternoon thunderstorm, and then a little bit more patchy fog tonight. Temperatures today, we could see as high as the upper 80s as the afternoon goes on. Otherwise, they'll be falling back into the 60s tonight. And then tomorrow, pretty much a repeat of today, although I think with more clouds in the afternoon and a greater chance for thunderstorms developing, a 30% chance that it probably won't get quite as high, but it'll still be very warm and very uncomfortable with the high humidity. And then for my 5-day outlook going through Saturday, Sunday, and Monday, you can see where the rain comes in on Saturday. Still some showers around on Sunday and then Monday, a few more, but it's starting to get a lot warmer as you go through Sunday and Monday. In fact, there's a good chance next week, as I go to the next slide for the extended outlook, that we could be looking at another heat wave with temperatures in the 90s again, which would be the third heat wave that we've had so far this season. And that's quite unusual, especially since it's only early July yet. Now I'd like to talk about the difference between weather and climate. Weather is the state of the atmosphere at any given time and place, and it's defined by the temperature, the humidity, atmospheric pressure, the wind speed and direction, sky cover, and the form and intensity of any precipitation, as well as any obstructions to visibility caused by that precipitation. Whereas climate is just a summary of the average long-term values of all of these conditions. And it's for any particular place, and it also includes the expected extremes and the frequency of these extremes that might occur over the course of a year. And climate is usually defined as a 30-year period when we take the averages of all the weather conditions. Now, as far as Maine's concerned, most of our weather comes from someplace else. A lot of people don't realize that, but all the air that comes into Maine is coming from either from Canada or from the Midwest or the Great Lakes, sometimes from the Southeast, sometimes off the Atlantic, and sometimes, in very rare occasions, all the way from the Pacific. We're on the east coast of North America, so that means that most of the air tends to come from the interior of the continent. And so that means it gets pretty warm in the summer and pretty cold in the winter. Now I'm going to show a map in a minute that'll compare us to Washington, which is at about the same latitude, but they have a much milder climate without a very cold winter or a very warm summer. And that's typical of the places that are on the west coast of a continent. Now, Maine also has access to all the different types of air masses that can come from the different parts of North America as well as from the ocean. And because of the way the storm tracks usually track across North America, most of the storms usually end up coming either near or through this area. And that's why we tend to have usually, or at least in the past, very changeable conditions. And one more thing, as far as our geography is concerned, we have a relatively cold ocean to the east and the southeast of us, mainly because of the Labrador ocean current that comes around Newfoundland and Nova Scotia and right into the Gulf of Maine. And we have a relatively low mountain chain across the western and northwest parts of the state that can temper some of the air that would come at us from Canada or from the Great Lakes. And here's a map of Maine showing these things. Here's the Labrador current as it comes around Nova Scotia. Part of it goes back into the Bay of Fundy, and part of it goes right along the Maine coast and right down to the Boston area. And that's why if you ever go swimming in beaches in Maine, even if it's in the 90s, the water is always fairly cold because of that cold Labrador current. And it has a bearing on the types of air that'll move into the state if the wind is coming in off the ocean. And here's a map of North America, and it's showing, here's Washington on the west coast and Maine on the east coast. And I've drawn these arrows. The blue arrow here shows how the tendency for cold air to come in from Canada. And also a thing to keep in mind is that the coldest part of North America at all times of the year is right here, the Canadian archipelago, which keeps a snow cover and ice cover for most of the year. And you also have the Greenland ice cap fairly close by too. So this all leads, yes. Okay, I'll keep going. This leads to this part of the continent staying cold all through the year. And whenever some of that air comes to our area, we tend to have our coldest temperatures in the winter. And even in the summer, we can get some summer Arctic air that would cool us off and we'd only be dry and in the 70s. Whereas if we have air that comes out of the Gulf of Mexico or up the East Coast, it tends to be very warm and humid. And that's exactly what we're having today, and looks like we're going to be having for the most part right through the next 2 weeks. And then you compare this to Washington, which is on the west coast, and the air tends to come in off the Pacific. If it's coming from the Gulf of Alaska, it tends to be relatively cool, but not cold. And if it's coming due west or from the southwest, it tends to be a little bit warmer and more humid, but not hot. And so that's why if you live in Washington, you tend to have a more temperate climate than if you live in Maine, even though we're at similar latitudes. Now, all weather analysis has to start somewhere, and it starts with observations that are made at all the different reporting stations around the world. And the data that comes from these observations is then plotted on a weather map. I've shown a typical station model here. And here's the temperature, 31 degrees. It's light snow, 26 dew point. The pressure is 998.7. With a southeast wind, it's cloudy, and it's 15 knots of a southeast wind. And here shows how you put all of these station models together on a map. Now, this was the map for 11 o'clock in the morning on June 30th. And I don't know if you remember back then, but we had a pretty clammy, cloudy day with some light rain and drizzle around. And that's because this weak low pressure system was sitting south of Nova Scotia and circulating air in off the cool and damp North Atlantic. And you can see how that circulation would bring that those cloudy conditions and the cool damp air into this area. And if you went further west, which is what we ended up having after a while, you see that it's a lot of clear skies here with high pressure here and here. And that's eventually what we had once these systems moved off. Now, the the main drivers and influences of weather, obviously the sun, because it's the main supplier of energy, which drives all the weather systems. And the Earth's spherical shape causes complex energy transfers. And this causes the surface of the Earth to be heated unevenly. I'll have a slide later on that points this out. And uneven heating is what causes the air to move. And I'll show why that happens in a few slides. And the rotating Earth also complicates these air movements. So they don't just go in straight lines. The rotation causes them to go in curved lines. And the presence of water in all its forms, whether it's a solid, liquid, or gas, also has an influence on energy transfer and complicates all the air movements. The shape and position of continents and the oceans has an influence, as does the type of land surface and the track of ocean currents. These all complicate the movement of air across the Earth's surface. Now we have layers of the Earth's atmosphere, and I'm sticking this in just so you have a background feel for, if you look up into the sky, this is what you see. You see this yellow bar here. If you look right up, you can see it. Well, I'm only kidding. But here's the top of the atmosphere. The solar radiation comes in, and this is fairly arbitrary. We say that the atmosphere peters out at about 36,000 miles up, and the temperature up there is minus 454 degrees Fahrenheit. And we call this layer here the exopause, or the top layer of the exosphere, which is where the atmosphere gradually peters out. Below that, we have the thermosphere, and this is caused by the sun's energy exciting all the few molecules that are still left up there, and excites them so that we have what we call the auroras, the bright lights that happen usually closer to the poles, but they've been known to occur as far south as the latitude of Florida in very rare occasions. And you'll notice that it cools off quite a bit once you go through the thermosphere. From 3,600 degrees Fahrenheit, where the actual molecules are excited, and then it cools all the way down to minus 134 Fahrenheit. So really big switch here in the course of only about 40 miles. Actually 400 miles. I mean. And then we have the mesosphere, and this starts to warm up again. And by the time you get to the stratosphere, you have much warmer conditions. The top of the stratosphere is about 28 degrees Fahrenheit. And the reason the stratosphere forms is because as the ultraviolet light from the sun comes down through the atmosphere, it reaches dense enough oxygen levels here that it changes them from the O2 form to the O3 form, which we call ozone. And this absorption of the ultraviolet light, or most of it anyway, is what causes or allows life to occur on Earth. Because if we didn't have that, life as we know it couldn't exist, because, well, you know what happens when you get sunburn, and you can get skin cancer from too much ultraviolet light. And imagine if we had the full amount coming through. And then last but not least, in fact, definitely not least, is the troposphere. And this is where all the weather happens. And it's only about 7 miles thick on the average. It varies from about 10, 11 miles at the equator to about 4 miles at the poles. But on the average, it's about 7 miles thick. And everything that we recognize as weather happens in this very shallow layer of the atmosphere. It's also the densest layer. And one more thing before I go on. The atmosphere is mostly nitrogen and oxygen, and only 1% of trace gases, but these trace gases are exceedingly important, because without them, we wouldn't be as warm as we are. We'd be more like the moon, because nitrogen and oxygen do not absorb solar radiation. They do not absorb infrared radiation that the Earth puts out. Only the trace greenhouse gases do. Now, energy transfer is all governed by the second law of thermodynamics, which simply says energy goes from a hot state to a colder state, or from a more ordered state to a more disordered state. You know that this is true when you put on a hot water faucet and a cold water faucet, and the water might be scalding hot out of a hot water faucet, but it's really cold out of the cold water faucet. You put them both on, and you end up with lukewarm water. And that's because nature is always trying to get rid of what we call energy gradients, or the difference between a hot state and a cold state, and make everything kind of bland. The three major mechanisms that cause energy to be transferred are radiation, and that's energy right through space; conduction, which is a substance, the molecules and atoms of the substance will vibrate, move, or rotate, and they'll transfer that energy by bumping into their neighbors. And then we have convection, and convection is probably the most important method of transfer that affects or causes weather, because this is when you have a fluid with different energy quantities in different spaces. The fluid tends to move, and I'll show you why in a minute. And it's the energy transfer as the fluid moves and carries the energy with it from one place to another. Now, as far as radiation in space is concerned, the hotter a body is, the higher the intensity and the type of radiation that it puts out. So, for example, the sun's surface temperature averages about 6,000 degrees Celsius or 10,000 Fahrenheit. So most of its radiation is put out in the shortwave infrared, in the visible, and in the ultraviolet. And it tails off on either end of that. The Earth, on the other hand, only has a surface temperature that averages about 15 Celsius, which is about 59 Fahrenheit. And so most of the radiation that the Earth puts out is long-wave infrared. And this is very important when we get into what keeps the Earth's surface warm, or habitable, I should say. Now, because the sun is a lot hotter than the Earth, the sun is what heats up the Earth and not the other way around. And that should be obvious. And again, that's the second law of thermodynamics that determines that. Now, as the sun's rays, which are represented by these yellow arrows, comes in through the atmosphere, as I said before, since it's mostly nitrogen and oxygen, it's transparent to the solar radiation that's coming in. And so it has a chance to go all the way down to the surface, where it heats up the surface of the Earth. And for example, if it heats it up to about 86 Fahrenheit, then using conduction, the molecules of the surface will bounce against those bottom molecules of the air and raise the temperature up, say, 77 or 80 or somewhere around there. Now, if we have what I call an idealized atmosphere with no movement and dry air, that is, no water in it, you can see how the conduction peters off quite rapidly as you go up in elevation. And by the time you get up to around 15,000 feet, if other things aren't coming into play, the temperature would drop off to minus 27 Fahrenheit. However, there are other things that come in play, particularly convection. Now, if we look at Earth's surface, and I said that because of the way the Earth is and the curvature of the Earth and the fact that the equator gets more heat than the poles, we have warmer surfaces and colder surfaces. So say we have a warm surface over here, the air above it will get warmer and it'll become less dense, and that'll tend to make it rise. And so as it rises, the air on either side of it will come in. And so you have this cycle beginning here where the air rises, and then it'll gradually cool off as it gets higher into the atmosphere until it hits the tropopause. And above that, remember we said the stratosphere, where the ozone layer is, that's where the air tends to warm up because of that ozone mechanism that's forming the ozone, absorbing all that ultraviolet radiation. And so it can't go any higher because this air tends to be colder than this air. So it'll spread out, going this way and that way, and then it'll continue moving over and cool off, and then it'll get to a point where it converges with other cooler air and it'll sink to a colder surface. And so you end up having this whole circulation pattern, this big circle where the air rises over here, spreads out, sinks over here, and then goes back. We call this a convection cell, and this is the primary cause of weather movement, and it happens at all scales, from global scale down to microscopic scales, and that's what causes all our weather, basically. A few more things before I go on. The surface here, because you have sinking air and divergence of the air, this is where you would have higher pressure. Over here, where you have a converging air and rising air, you have lower pressure. It's just the opposite as you get up near the tropopause. You tend to have higher pressure over the surface low and lower pressure over the surface high. And that's pretty much the driving mechanism, as I said, for everything that goes on in the atmosphere. One more thing about heat capacity, and that's how much energy substance can hold and how fast it would heat up and cool off. And it turns out that water has the highest heat capacity of any substance that we know. It's been designated 1 calorie per gram for every degree Celsius that the water would either warm or cool. And this is 3 times more than the average surface heat capacity. So this means that it takes 3 times longer for an ocean or any water body to warm up and then to cool off than it does for a land surface to warm up or cool off. And that's why if you live near the ocean, your day and night temperatures don't change that much, and the same thing goes for seasonal temperatures. In fact, if you live in an island, I was up in Iceland for 1.5 years when I was still in the Navy, and there's very little difference up there between summer and winter, and it's fairly mild all year round, despite its high latitude. But if you go to a place like North Dakota, which is right in the middle of North America, and it's all land surface, and it's very flat and tends to absorb solar heat very quickly and lose it very quickly at night. They tend to have a big difference between day and night temperatures, and also between summer and winter. And that's the reason for it, is because the high heat capacity of water. And one last thing, as far as water is concerned, there's a lot of energy that's involved in making ice melt and making liquid water evaporate into a vapor. And it takes a lot of energy to go in this direction, and it also releases a lot of energy when you go back this way. In other words, if you condense the vapor into a liquid, or if you freeze a liquid into a solid, you release a lot of energy to the surrounding air. That's very important when we're talking about heat transfer in the atmosphere, because this is continually going on. Whenever you see a cloud building up, this is releasing energy to the surrounding air around that cloud, because in order to have that cloud form, you have to condense vapor into tiny liquid water droplets. You can also go directly from ice to water vapor, or from water vapor to ice. And a good example of this is if you have frost in your windshield on a chilly morning. That's because the water vapor that was available went directly to crystals, ice crystals. And in doing so, it released even more energy, 677 calories per gram. Now, an overview of water in the whole weather system, things to keep in mind. It's the only substance that can exist simultaneously on Earth's surface and in the atmosphere at a relatively narrow range of temperatures. So you can have solid liquids and gases of gaseous form of water existing all together at the same time, and in a very narrow range of temperature. And it's continually changing state, depending on how energy is being transmitted, absorbed, or emitted through that little blob of water. And it's also the single most important substance in heat retention, as I already pointed out, and also in transferal, because of its high heat capacity and those big latent heat changes when it changes state from a solid to a liquid to a gas and back again. Also, snow, ice, and clouds are the greatest reflectors of incoming solar radiation by far on the Earth's surface. Most of the solar radiation that comes in is reflected by these 3 things. And most atmospheric water vapor occurs from the evaporation of ocean water. Now, you might have some coming from a large freshwater body like the Great Lakes, but in general, most of the water vapor in the atmosphere comes from the ocean, which absorbs about 80% of all incoming solar radiation. And condensation of water vapor into cloud droplets can only occur if you have uh, condensation nuclei. And believe it or not, you need sort of a dirty atmosphere in order to have cloud droplets form. You need salt, dust, or soot particles floating around because there just is not enough water vapor available in most situations. You have to have something to nudge them together, and that happens when you have these little particles that they can attract water vapor, and then they'll start accumulating and become a liquid or a frozen form on these condensation nuclei. And then we also have two major precipitation mechanisms called coalescence or accretion, and I'll go over those in a second. I'm not going to go into too much detail on those because it would probably take me the whole hour just to explain how each works. But just know that in most situations, we have cold air at the surface, represented by these blue arrows, and warm air riding aloft over it. You have what are called stratus-type clouds. And these are considered to be horizontal formation clouds. And there are various categories of them. You have regular stratus, which is fairly low altitude, and then you go up a little higher, and they're called altostratus, and then cirrostratus up at close to the tropopause up here. And above that, you might have little wisps of ice crystals called cirrus clouds. And wherever you have accretion occurring, where you have snowflakes forming and then either falling as snow all the way down or melting on the way down to fall as rain, we have what we call nimbostratus clouds. If you see the term nimbo, that means that it's precipitating from it. Now over here in the warmer section, if you have a lot of heating, you'll have these puffy clouds, which we call cumulus clouds, form. And if they really get going, they'll develop all the way up into a cumulonimbus. And this is what will cause a thunderstorm or heavy shower or even tornadoes in some situations. And you'll notice that the cumulonimbus goes all the way up to the tropopause, and many times will actually break up into the stratosphere, where the jet stream will just rip off the tops and below the cirrus downstream over here. And then finally, you have a combination of both stratus and cumulus called stratocumulus, and this usually occurs behind a front that is passed. And again, it's a mixture of both vertical formation and horizontal formation. So if anybody has any more questions about cloud formation, just you can ask me after. Then we go to circulation systems. There are actual formal ways of recognizing all the different circulations that occur in the atmosphere. First of all, we have what's called the general circulation, and this takes in the whole atmosphere. That includes things like trade winds, westerlies, Hadley cells in the tropics, and also the jet streams. Then we have secondary circulations, and these are more regional, and they include cyclones and anticyclones, which are low pressure and high pressure systems, and their accompanying fronts. And these systems are superimposed on the general circulation. And finally, you have the tertiary or local circulations, and these include things like sea breezes, land breezes, mountain valley breezes, etc. And these are superimposed on the secondary circulation. Now, here's that picture I promised you about showing how the direct solar radiation is in the tropics from about latitude 30 north, 30 south on the average, or the course of an average year. And this is where most of the heating takes place, in this area. And as you go further towards the pole in either hemisphere, you'll notice that the angle gets sharper and sharper until finally, right at the North Pole or the South Pole, it just glances right over the pole, and you hardly get any effect of the radiation at all, hardly any warming at all. And because of that, you have this general tropospheric circulation. And again, this would probably take the whole hour to explain this whole picture to you, but I'll just give you just a brief, the important points here. Here you see at the equator that the air is rising because that's the hottest surface area. And it'll go up to the tropopause, and then the air will spread both north and south. And eventually this air will end up all the way to the pole in both hemispheres. However, you'll notice that the surface area, as you go along the surface of a sphere, gets smaller and smaller. So all the air that was in this very large area of the equator has to go somewhere. So because they can't fit going this way back towards the pole, because the surface area of the Earth gets smaller as you go towards the poles, some of that air starts to sink here. And it does it both hemispheres all over the world. And that's at about 30 degrees north and 30 degrees south. And that coincides where all the great deserts of the world are, because you tend to have high pressure over these areas. And high pressure means you're having evaporation of any moisture, so no clouds, no rain, and you have deserts. And the air that reaches the surface would spread both back to the equator and towards the pole along the surface. And this would be what we would consider to be the prevailing westerlies in the mid-latitudes. But you'll notice that air that was sinking here at the pole is also coming down, and it eventually meets up with these westerlies that are coming up from the subtropics. And because this is a lot colder and this is a lot warmer and more humid, they don't mix right away. In fact, they form a boundary, which is practically impenetrable. And we call this the polar front. And this is where all the storms in the mid-latitudes occur, along this polar front. So that's important to remember. And also to remember that this polar front designates the boundary between the cold, dry polar air and the warm, moist tropical air. And this is where all the storms will form along this boundary. And it occurs in both hemispheres. Now, when we talk about these different types of air, we usually designate them as air masses. And that's air which has similar properties throughout the whole mass of air. And I'll show you another picture that shows this over North America. And where two different air masses come together, for example, at the polar front, we have what's called a stationary front if the front is not moving. And there's discontinuity in all the properties. So in other words, it's cold on one side, warm on the other side. Dry on one side, humid on the other side. The winds might be north on one side and south on the other side. And it's just an abrupt change. And that's why whenever a front goes through you, you'll notice there's an abrupt change in all the weather conditions. Now, if the front is moving from warm to cold, we call it a warm front. And this boundary shows the warm air overriding the colder air out ahead of the surface front. And that's usually what causes a lot of steady rain or snow to fall ahead of that front. And then a cold front is when you have the front moving from cold to warm. And because the cold air is denser, it'll dig in under the warmer air, and it'll cause a lot of cumulus type clouds, the big puffy clouds, and that's usually where thunderstorms form. And if you have really extreme conditions, you can have tornadoes also form in that ahead of that cold front. An occluded front occurs because cold fronts tend to move faster than warm fronts. So when the cold front eventually catches up to a warm front, it ends up pushing all the warm air aloft so that there's only cold air at the surface. But you can still have precipitation falling from that warm air aloft, that warm humid air aloft. And so you can still have some weather occurring even with an occluded front. Now let's look at some air masses over North America. We have Arctic air, which you'd expect to be up here near the pole. That's the coldest air that we have in North America. Remember I said this is the coldest area of the continent. Then you have continental polar air, which is usually the stuff that affects us in the winter. But you also have maritime polar air that comes in off the Atlantic, and that affects us, especially when a low pressure system will be moving off the coast and it'll give us rain or snow. And we have maritime tropical air that comes from the Gulf of Mexico and the subtropical Atlantic. And that air can come up the coast or come from the Mississippi Valley across the Midwest and into New England. Then you have continental tropical air, which is actually maritime tropical air from the Pacific, which has lost all its moisture as it crosses over the mountains here in the Southwest, and it dries out. And this can be the hottest air that we'll see in North America, this modified tropical air that becomes continental tropical. You also have a little bit milder air that comes in off the Pacific, modified Pacific air. And when this air manages to cross the entire country and reach us, we have probably most delightful conditions here in Maine. And I'll quickly show you what a warm front cross section looks like. Again, the tropical air rides up and over the colder polar air. Depending on what the temperature is here, you'll have either rain, snow, freezing rain, sleet. And freezing rain and sleet form when you have different layers of hot and cold air that because of the way the circulation is at different elevations. You might have a wedge of warm air here and a wedge of cold air here and another wedge of warm air here, and that would cause sleet. If you have it reversed so that you have the cold air on the surface, you'd have freezing rain. So it gets a little complicated, and again, it took me a long time to explain the whole thing, but just know that when you have a warm front like this, you can have all those different types of precipitation falling as that front approaches you. And then the cold front, you see the cold polar air digging in under that warm tropical air, and it forces that warm tropical air to go up, and you have extreme vertical motion occurring here. And the more extreme that vertical motion is, the bigger the cloud will form, and the more powerful the thunderstorm that develops will be. And as I said before, in very extreme situations, you can actually have tornadoes form if you have any rotation in this cloud. You'll have it's called a mini rotating cloud, and that might be just enough, give enough momentum with enough updraft here for a tornado to drop out the bottom of this and start to do its thing. And that'll all happen ahead of the cold front. Once you get behind the cold front, though, the skies start to clear off. You might have a few stratocumulus and little puffy cumulus, or even alphacumulus, but it eventually will clear off as that colder, drier polar air moves in. And here's a warm occlusion. And the reason I call it a warm occlusion is because, you see, the cold air or the cold front caught up with the warm front and forced all the warm air aloft. But this air, even though it's colder than this air, it's not as cold as this air, which is out in front. So it acts like a warm front here. So you could have warm front precipitation, and that could occur at any place along this whole boundary. On the other hand, if you have a cold occlusion, this air here is a lot colder than this air, which is still colder than the air that got shoved aloft. And so you tend to have more showery precipitation because of this, because this cold occlusion would act more like a cold front. Now we go to low and high pressure. A cyclone is the name given to any circulation that has the lowest pressure at the center, and it spins counterclockwise in the northern hemisphere, clockwise in the southern hemisphere, and it usually causes very stormy conditions. Anticyclone would be just the opposite. Any circulation with the highest pressure in the center, and this is what we call high pressure systems, and they spin clockwise in the north and counterclockwise in the south. And because the air tends to sink in these things and evaporate any moisture, we usually have very fair conditions with them. Now, I apologize for making such a busy map, but I got carried away here. But what I'll do is I'll just concentrate on Maine. Here's Maine right here. And this would be a typical winter circulation pattern. And you'll see that there's a low pressure system that's sitting just off Nantucket, and it's causing a flow in off the Atlantic, and you have an east to northeast wind blowing in across Maine. So as you would imagine, we're probably having snow here in central Maine with a situation like this. Notice also how the jet stream, which is represented by this thick purple line, it's moving up from the southwest to the northeast. And the more moisture that this jet stream can pull up out of the Gulf of Mexico, the bigger the snowstorm we're going to have. So believe it or not, you can thank tropical air riding up and over the surface low pressure system for our biggest snowstorm. Now, as this system moves away, we'll get into this high pressure that's building in from the Great Lakes, and that'll clear us off and bring colder air back in. But because of the way this pattern is with the jet stream like this, we'll probably end up in another day or so with this next system moving through and doing the same thing, or slightly different depending if there's any little wiggle in the path of this jet stream. Now you go to spring and you notice it's still quite a busy pattern here, but you'll also notice that the jet stream is further north. And this occurs because you're having very rapid warming and expansion of the subtropical high pressure zones up into the United States and up into these parts of the Atlantic and the Pacific. So you've got very warm air starting to move in, but you still have reasonably cold air that's still sitting up over Canada. So that's why we can here in Maine go from the situation where we might have snow the way we did on, I think it was April 12th, and that was our biggest snowstorm of the season. And then a few weeks later, we ended up with a heat wave in the 90s as we got into Maine, because back when we had the snow, we were in the cold air, and then a few weeks later, we got into this really warm air that jet stream actually did this, went way up into central Quebec. And so we had a lot of hot air coming here, which is very possible during the spring. But you can have a lot of extremes occur in the spring. And as I said, you can go from hot to cold and back to hot again, and then even back to cold again, which we ended up doing on June 1st when a lot of people had frost after we had 90s the week before. And in summer, you'll notice that the jet stream tends to remain up in Canada. And that's what we're seeing right now. And notice what happens. Here you have these big high pressure systems, usually to the south of us, and they're pumping this warm, humid air up into New England. And as I said, we're seeing that now, and we're probably going to be seeing it for the next 2 weeks at least, if not longer, as it looks like all the long-range models are keeping the jet stream up here in Canada. Also, you'll notice we can start to see hurricanes forming, mainly in the Gulf of Mexico in the early summer, and also here off Baja California in the Pacific. And you'll notice as we get into fall that the hurricane track tends to form more along the east coast of the United States. And that's why as we get into late summer and early fall here in New England, that tends to be a possibility for our hurricanes to affect us during those months, anywhere from late August to even early November, as they track usually like this. But you'll notice also that the main polar jet is also a little bit further south, and so we'll have more incursions of colder air coming in. But we can still get quite warm right through the fall. In fact, even into November, we can have pretty balmy conditions here for at least a few days, and then it'll flip over and we'll get back into colder conditions and back and forth until we finally get back to a winter situation as we get into December. Briefly, I'm going to go through some local circulation patterns. I've listed a whole bunch of them here. These are all very small scale circulations. Probably the most well-known, especially if you live near the coast, is the sea breeze. And for example, right now, we're in the mid to upper 80s here in central Maine. And if you go to Bar Harbor or to Rockland or a place right on the coast, they're probably in the 60s right now because they've got a sea breeze blowing that cooler ocean air into them. And tonight it'll reverse and they'll have a land breeze, which will actually warm them up a little bit. And then there are other things here. We have mountain breezes, valley breezes, glacier winds. Wind can be funneled through buildings and canyons. Also, tornadoes can form if you have violent updrafts. So as I mentioned, when we were talking about thunderstorms and cold fronts, you can have water spouts if they occur over water. You can have what we used to call squall lines, but now they call them derechos, which are lines of very strong winds. Can also occur with strong thunderstorms, and they occur ahead of a cold front. And then you can have very small scale whirlwinds, which we call dust devils. And they're sort of like a tornado, but they don't have the complete mechanism that a tornado has. And they occur only if you have a very hot surface that will cause updrafts, and a little bit of spinning will occur. That'll all of a sudden it'll just cascade and become a dust devil. And I remember one time when I was still coaching track at Dexter, we had a meet up in Millinocket, and all of a sudden one of these dust devils formed right on the football field where we had uh, our base of operations, and they went right through and blew everybody's equipment all over the place. Uh, and they happen under clear skies, by the way. And if it happens over water, we call it a pseudo water spout. And here's a depiction of what a sea breeze would look like. So the land heats up, the air rises, and it allows the air to come in off the ocean. And you have this complete cycle here. And that'll happen as long as this land is a lot warmer than the ocean is. But at night, the land will cool off, and the ocean doesn't change much. And so that'll be warmer than the land, and you'll tend to have the air rise over the ocean, and that'll cause the air off the land to move in this way. So we call that a land breeze, and they happen at night. Now, let's look at the global climate and how it affects Maine. Now, there shouldn't have been any controversy over these things, but over the last 30, 40, 50 years, because of special interests, mainly in the fossil fuel lobby, there has been some controversy over this, but among scientists, there is no controversy whatsoever. The main drivers of climate, the principal one, obviously, is solar output. The sun provides all the energy, so that's what causes the energy that gives us our temperatures and also drives the weather systems. But you can have slight variations in the Earth's orbit around the sun, and this can cause differences in heating, which will also cascade and give you differences in the climate. And I'll explain that in a second, how that works. And we call these Milankovitch cycles because Milutin Milankovic, which was a Serbian mathematician who was, I think he was a prisoner of war under the Austrian government in World War I. And when he was in prison, they asked him if he needed anything. And he said, yeah, could you give me pencil and paper? And so we worked out in prison the first mathematics that told him about the orbital variations and how they could affect how much energy comes into the Earth and affect the climate. Then we have the Earth's albedo, which is the reflection from the clouds and ice and light surfaces. We have greenhouse gas concentrations, and we can look at greenhouse gas concentrations, especially carbon dioxide, as being the thermostat that controls everything else. Because the carbon dioxide turns out to be a very stable and long-lasting gas, and it only takes minute quantities of it to absorb just enough energy so that it starts tilting the whole system to either warmer if it increases or colder if it decreases. And that's where, remember when I talked about, I'll get to that in a minute. And we also have water vapor, methane, and nitrous oxide. The water vapor is definitely a multiplier of the carbon dioxide. Methane can be a multiplier, and it's very important because methane is extremely efficient at absorbing infrared radiation, as is nitrous oxide. And these things can be multipliers if they're released. For example, if you melt permafrost, you can release methane. If you have a huge cattle operation like they have out west in the plain states, there's a lot of methane that comes from those cattle operations. You have methane that leaks from oil wells and from gas wells. So all those things can increase the methane in the atmosphere. And then finally, you have the position of the continents and ocean currents. But as far as we're concerned, these aren't important because these are very long-term changes that occur. And so as far as these would occur over tens of millions of years, so we don't have to worry about that. But these are the four drivers that we're concerned with. Now, I was going to talk about positive and negative feedbacks. Remember when I said the CO2 might absorb just a little bit more, which would cause a little bit more water vapor to evaporate off the oceans, and that would increase the absorption of infrared radiation even more, which would then increase more evaporation and et cetera, and it goes around in a cycle. And that's called a positive feedback. And then as the polar ice caps melt, they expose more open ocean, and that also causes more warming, which then causes more of a feedback, which causes more warming, and it keeps going and going. Now, if you have a situation where a certain mechanism will damp down those processes so that instead of, for example, let's say you have more clouds forming, that will reflect low clouds that will reflect solar radiation. That's considered a negative feedback. So that'll keep warming from getting out of hand. But then you have what are called tipping points. So these are critical areas or critical points in this cycle of warming or cooling, beyond which you can't return. You'll go to a new state. And there's been a lot of controversy, especially about these tipping points, because a lot of scientists haven't been able to figure out just where they were or where they are. And there is some school of thought that says we've already passed tipping points and there's no turning back to a colder climate, and others that are still skeptical that we've reached those tipping points yet. So the verdict is still out, and we'll see what happens. Personally, I tend to agree with the ones that think that we've already passed the point of no return, but that's my opinion. Now, as far as solar output goes, there's a slight fluctuation in solar output. Usually it goes with the 11-year sunspot cycle. So if you have a lot of sunspots, there's more activity, so a little bit more energy coming in. Fewer sunspots, a little bit less energy, so a little bit less activity. But they really hasn't really changed that much. And we don't have to really worry too much about major changes in the solar output. There is some speculation that an extended dearth of sunspots during the 17th century led to the Little Ice Age, but there's still some controversy over that idea. Now, the solar radiation, when it hits the top of the atmosphere, we consider it to be 100%. But as it comes down through the atmosphere, remember we said that most of the ultraviolet gets absorbed in the ozone layer. That's about 9% of all incoming radiation. Another 4% gets absorbed by other things like maybe clouds or dust particles or aerosols or anything like that. And 36%, a full 36% actually gets reflected by clouds and ice sheets and other reflective materials. So that by the time that solar radiation makes it all the way to the surface, it's just a little more than half of that, whatever came to the top of the atmosphere that makes it to the surface. But that half will heat up the surface. That's what causes the surface to heat up the way it does. And because whatever comes in has to go out in order to keep a balance, the Earth's surface will re-radiate at a much lower frequency, much lower energy level in the infrared, the long-wave infrared. And so that 51% gets sent back out into space. Along the way, it picks up that 4% that's radiated also back out into space by various things, plus the 9% of the ozone layer that also gets radiated back out. And eventually you have 100% goes out into space, but it's of a very low grade of energy compared to what came in from the sun. Now, if this 100% here does not equal 100% here, then you're going to have either warming or cooling. For example, you have 100% coming in, but you only have 95% going out, you're going to have warming. If you have 100% coming in and you have 105% going out, you're going to have cooling. It's as simple as that. That's what causes the climate to warm and to cool. Now, the Milankovitch cycles, one of the cycles concerns the shape of the Earth's orbit. Usually it's elliptical, but it can contract to almost a perfect sphere, and it can become even more elliptical than it is now. And this takes about 100,000 years for this whole cycle to occur. And this is considered to be the major Milankovitch cycle. Also, you have the tilt of the Earth's axis. Here we're about 23.5 degrees right now, but that obliquity, as it's called, changes from 21.5 to 24.5. And that occurs about every 41,000 years. And then we have the wobbling of that axis, and that occurs about every 21,000 years. Right now, the North Pole tilts towards Polaris, but in 21,000 years, it'll be tilting the other way to another star, which I forget which one it's going to be, maybe Vega, but I'm not sure. And then 21,000 years after that, it'll be back at Polaris. And all of these motions taken together have an effect on how much radiation comes in during the northern hemisphere summer. And that's the key that determines whether we have an ice age or not. If we have less energy coming in during the northern hemisphere summer, where most of the ice would be, then the ice sheet would tend to grow as it did 40,000 years ago and reached its max about 20,000 years ago. And then as the heating goes back up during the northern hemisphere summer, we have an interglacial. We have a thawing of that ice sheet, which happened after 20,000 years, and we reached the maximum about 8 to 10,000 years ago. Now, we should have been cooling off and heading towards another ice age over the next few tens of thousands of years, until humans started burning fossil fuels back in the 1700s on a large scale. But we'll get into that in a second. The Earth's albedo, a few things to know. We have the open oceans absorb up to 90% of the insolation that comes in from the sun. And white snow and ice, notice I said white snow and ice, because dirty snow and ice don't reflect this much, up to 90%. Light land surfaces will also reflect insolation varying degrees, and dark land surfaces will absorb them. Clouds tend to reflect up to 90%, especially if they're low clouds. High clouds, not so much. In fact, high clouds tend to be transparent to a lot of solar radiation. And you probably noticed this. You'll have a very high overcast of cirrostratus clouds, and you can still see the sun. It's kind of hazy looking, but you can still see it. That means some of that energy is getting through. Vegetation also tends to absorb and hold a lot of solar radiation because of all the water that exists within the plant. And also, they're usually dark color. Green tends to be a good absorber. Then you have bare ground, human infrastructure, all our buildings and roads. They tend, because they don't have any water in them, they tend to absorb very quickly and emit very quickly. Then we have greenhouse gas concentrations, and I'll just let you look at this. We're up to 415 right now. When I first pulled this chart off from a publication, this was back in 2011, and we were 391. We're up to 415 now in 2020 of CO2. And same thing goes for methane. We're up over 2 parts per million now. And for nitrous oxide, we're up almost to a half part per million. So all of these greenhouse gases are going up. And there hasn't been any hiatus since we started tracking this back in the 1950s. The track is just up, just like that. Now we come to water vapor, and because water vapor is so highly variable, depending whether it's uh, evaporating or condensing back into clouds or whatever, its effects are very variable. But the higher the water vapor content, or the more humid the air is, the more energy it's going to hold. And it holds it in all different wavelengths, not only infrared, but also into the visible and ultraviolet. So it's got a very high heat capacity in all its phases. And when it condenses from a gas to a liquid, it releases an enormous amount of latent heat that also warm up areas around wherever that cloud formation is occurring. It's been estimated that 7% increase in the average water vapor content occurs with each degree Celsius increase in average atmospheric temperature. So when this chart was made, we had about a 4% increase since 1970, and that's up to about a 5% increase now. All right. And again, as I said before, the main causes of a changing climate are if any of these things change. If the solar radiation changes, the greenhouse gas concentrations change, the albedo changes, or the variations change. If radiation decreases, we're going to get cooler. Greenhouse gas concentrations decrease, we're going to get cooler. And it doesn't matter what reason causes them to decrease or increase. And the same thing for albedo. Doesn't matter what causes the albedo, the reflection, to increase or decrease. If it increases, then we cool off. If it decreases, we warm up. If the greenhouse gases increase, we warm up. If solar radiation increases, we warm up. And the Milankovitch variations, they're going to continue doing what they do. So as I said before, we were on track to cool off over the next few thousand years and go back to another ice age, but that's not going to happen then, because we've cut off the cooling that the very minute Milankovitch changes cause. Now, why is this cooling or warming very important to what happens to our weather? Well, it turns out that a cooling or a warming affects the polar jet stream. And the reason for this is the jet stream forms because of a contrast between the equator and the pole. So the less of a contrast you have, the weaker the jet stream is, and the more it starts to meander. And it'll even form blocks, which we all have to admit have become more common over the last few decades. Now here's a depiction of the polar jet. You see this purple line is the polar jet, and this is looking down at the North Pole. Here's the equator. Here's 45 degrees. This is where we live. And you'll notice that with a cold North Pole or a cold Arctic, it's fairly what we call zonal flow. It's fairly smooth flow around the pole, and a lot of it dips below our latitude. This is what you typically would see in the winter if we have a very cold Arctic. Now, if the Arctic warms up, whether it's in the summer or whether it's from global warming generally, you'll notice that the jet really weakens and becomes more meandering. And in fact, you can get to a point where you might have, this would be considered a blocking high. This would be considered a cutoff low, another blocking high, another cutoff low. And these things don't move, especially if they become blocks. They'll just sit in place sometimes for weeks or even months at a time. And when that happens, that's when we have our extreme conditions. And that's why a weakening jet stream is so very important to understand and to prepare for more extreme conditions happening. Now, here's a more detailed example of a blocking pattern over North America. Here's what's called an omega block. And if you use your imagination, you can see the Greek letter omega here. So this is a high pressure system at all levels. Here's the upper air, here's the surface. They're pretty much stacked on top of each other. And when that happens, nothing moves. So you'll have a cutoff low right here with cooler conditions and stormy conditions that won't move. So if you're living in Minneapolis, you're going to have torrential rain that's not going to change for maybe a week or two. Same thing goes for over here. If you're off New Jersey and southern New England, and maybe even up into Maine, with a low pressure cutoff here, it's just going to continue to pull moisture in and dump rain over us. If you're over here, you're going to have a heat wave. It's going to be unseasonably warm in most of Ontario, very dry. And if this doesn't move for a few weeks, they're going to have a drought. And these are the situations that we're seeing more and more of as the jet stream continues to weaken. And it's been weakening in all seasons. Right now, about as weak as I've seen it in early July. Now, this is in comparison to a more so-called normal zonal flow. See the jet streams like this. It's not cut off anywhere. Fairly smooth pattern. So if you have a storm system moving by here, okay, it'll rain for a few hours. This will move on, get into some dry air. And then maybe another day or two, another system will come by, give us another little bit of rain, move on, get into some more dry air. So it'll be a much more changeable situation. But we're not seeing that much anymore. So most of the effects that we've seen here in central Maine over, I'd say, the last 30, 40 years can be broken down into these points. We've had milder and cloudier winters for the most part. Any Arctic outbreak that occurs doesn't give us as cold temperatures as they used to be. I remember when I first moved to this area back in the early 1980s, it was nothing to have at least some minus 35 or 36 once or twice during the winter. We haven't seen that, I'd say, in at least 20 years. In fact, some years we hardly get below zero or hardly get below minus 10. That's how much milder it's gotten in the winter here. However, because you can have blocking systems that will keep a certain situation for days or weeks at a time, you can have an extended Arctic outbreak so that you have a cold spell that'll last for a long time. So it might seem like it's a brutally cold winter because the cold spell is lasting so much longer than it used to, but it's still doing it with air that's not as cold as it used to be. And that's because it's just not that much cold air left up in the Arctic the way it used to be also. In the old days, it would be nothing to have minus 50, minus 60 up around the North Pole. Now they'd be lucky if they hit minus 20, minus 30. Now, a tendency for more rain and freezing rain to fall in the winter as the pattern gets milder and right into early spring, although you can still have big snowfalls. In fact, if the pattern sets up just right, you can still have tremendous snowfalls, but it'll be the kind of that heavy, wet snow that sticks to everything and causes all that damage, like we had in April. And there have been a lot more instances where we've had rain, freezing rain, because you'll have the structure of the atmosphere over us is such that it'll cause any snow to melt into raindrops, and then we'll have a layer of cold air into the surface that'll freeze up on contact. That's when you get the freezing rain. And you have more volatile springs. In other words, big swings from hot to cold and back again, as we've seen this past spring and early summer. And even though we can have early season heat waves, we can also have late frosts because of this volatility. And we saw that this year, as I said, on June 1st, a lot of people had a frost. And all forms of precipitation that do come tend to come in more intense clusters rather than spread out. Remember, I showed you when we had the zonal pattern that one system will zip right by and then have a break, and then another system will zip right by. But now we tend to have systems that just stall right over us for long periods of time. And if we're on the dry side, we have a drought. If we're on the wet side, we have mold growing on everything and floods and things like that. Now, our summers also tend to be warmer but cloudier, especially at night. And we have more stretches of hot conditions that can be strung together for longer heat waves. And we've seen that also this year. And rain can be very sporadic. And it's funny, one of my farmer friends, some of you probably know him, Gene Ripley in Dover Foxcroft, he's always hoping for rain for his crops. and he's always sending me messages. He's one of my clients, and always overjoyed when he gets enough rain. And he's always amazed that he might get an inch, and I might get a quarter of an inch, and it might be vice versa. And it all depends on who's lucky to be under the heavier rain shower in the summer. But that's becoming even more sporadic. Who gets rain and when, and how long it is, and how much rain it is. And then we get into the autumn, and they're tending to be warmer, with the warmer conditions lasting longer into the autumn. It's not unusual to have fairly balmy conditions right into November, for a good part of November. And that would push the dates of the first frost further into later in October or even into November some years. And I know a lot of places around here. I know one of my friends in Dover, she used to have her first frost at the end of August. And that's not happening anymore. Now she gets them at the end of September. She happens to be in a little low valley that where the cold air collects. But that's going to actually change as time goes on too. It'll be later and later first frost occurring. We can still, if we have a little cold snap moving in, we can still have an early snowfall, maybe even in October. And if we have it in November, and the pattern as we get into winter sets up just right, we can have just what happened last year, where we had a snow cover, I think it was middle of November, and it lasted all the way into the middle of April. And that's not because we had a very cold winter. In fact, we had a pretty mild winter, but it stayed just cold enough to keep the snow from all melting. And I'm going to finish up with 3 quick slides here about what's going on at my house here in Garland. And you can see how the temperature, this is the average temperature for the whole year, each year starting in 1985 when I started keeping track of this stuff. And we were around 42 degrees, the average temperature for the whole year. And as we went up through time here, we get towards the present time, the average temperature is getting up close to 45. But you'll notice that it was very changeable from year to year. But notice how that change is occurring. It goes up a little bit further and then comes down, goes up a little further and down, then further still, and then down, and then a little bit further, and then down, and then back, and then down, and then way up. In fact, I did a little analysis this morning, and I checked just how far above normal we've been so far this year. And the January to June average temperature is 7.1 degrees Fahrenheit above normal for a typical January to June period. And if this continued for the rest of the year, we would end up with 51.5 as our average annual temperature, which is off this chart. And that shows, even though there's a great volatility from year to year, because the trend is up, even if you get way cool the way we were last year, it's going to come back at us and get way warm the next year. And that type of situation, that volatility going way up and down, looks like it's going to continue for the foreseeable future. There's also been an increase over this period in total precipitation. And you'll notice we used to be around 45. In fact, if you go back to the early 70s, our average annual precipitation here was around 41 inches a year. Now we're up about 55 inches a year and climbing. And this was only 2011, and I haven't extended this out yet. I should do that, I guess. And I'm sure that we're even higher than that. And back in the early 70s, 55 inches a year would have been more like Georgia. So that shows just how much the increase in moisture has been in the atmosphere and how much more rain and snow we're getting up here. And finally, this will be the last slide, and then I'll take some questions. James Hansen, who's a famous scientist, he used to work at the Goddard laboratory from NASA, and also was a professor. In fact, he's a professor emeritus at Columbia University right now, and working with his associate Maki Kosato, who's still at Columbia. They did an analysis of the shifting patterns of temperature in all the northern hemisphere land areas from the period of 1951 until the present time. And they looked at the 30-year period, use that as their baseline. So back then, you had 33% of the time you're a little warmer than normal, 33% of the time a little colder than normal, 33% of the time you were pretty normal, and there was hardly any extreme. Now we get through the period from 1987 to 97, and you see that's all shifted over, and you start getting more extremes on the hot end. And it continues all the way up to the present time. And just look at the difference that we have now. This is worldwide now in the whole northern hemisphere, all land stations. So we're definitely seeing a warming trend. Global warming is definitely identifiable by any measure that you use. The Earth's climate is definitely warming. And that's my slideshow.
Great,
Well,
thank
are there
you.
any questions?